Okay, let's get going here. All right, good morning. I'll go ahead and get started here. So, I'm still working on the assignment 3s, getting those back. I got through about half of them, but I didn't want to give them back to everybody yet. So, I think so I'll probably review those a little bit maybe on Thursday. I should have them back to everybody by then. So, it looked like everybody had turned in something and had mostly gotten there. So they were looking pretty good, the ones I'd been able to get to. So looking ahead, we've got this week, we're going to stick with, well, we're going to look at logistic regression. So if you haven't looked at the notebook yet, I'm mostly going to look at that today. There's just one notebook this week here. And then coming up next week, it's the week before spring break, and we are holding our midterm test next week. So I'll be reviewing some stuff next week about the midterm test and other stuff like that. So yeah, we'll go over the logistic regression today, maybe review the assignment 3, and then we'll get into overall review for the stuff we've done so far and talk about what will be on the test starting next week, in case anybody had any questions about that. So, all right, check something here real quick. Okay. All right. Okay, so yeah, probably we might end up doing pretty much all this notebook today, but I wanted to say a few things about the logistic regression. So we will use logistic regression later on. Our next assignment isn't going to be. We'll get started on that after we come back from spring break. So at this point, you've just got to be thinking about the midterm test next week, and then have a little break. So logistic regression. If you've been doing the materials that we had for the past 2 weeks, went into linear regression and in some detail. So I hope you understand at least a little bit of the details of how it works in terms of defining a cost function and then using something like gradient descent, so using some optimization method in order to find the minimal place where the set of parameters give you the lowest cost for your function, right? So the nice thing about that is if you understand the basics of how that works, we can apply that same method to doing a classification problem with a few tweaks, okay? So as kind of a reminder here, so we're jumping back to talking about classification for a little bit here, right? So we want to look at logistic regression. As I've said before, it's a little bit of to me, it's always a little bit of a misnamed kind of a thing. It's got regression in the name, but logistic regression is really kind of the basic method for doing a classification task that we'll look at, okay? So, but the details of how it works, besides a few tweaks, is basically the same as the linear regression, okay? So as we'll see, or as you should have seen if you looked at the notebook yet for this week here. So the basic difficulty is, so for a regression problem, our targets, our labels is some real valued number, right? So the output function, the thing that we were trying to do by doing a linear combination of each feature multiplied by some parameter, the slope parameter, was some number, and we really didn't want it to have any kind of a limit or a range, right? So if we wanted to predict house prices, we needed it we needed it to be able to range from maybe $50,000 up to $1 million or something like that. right? So the basic problem, if we want to use the same idea for logistic regression, is first of all, our output is going to be more constrained, right? So, and as usual, when we're talking about classification, we'll start with the simplest case, a binary classification. So if we're trying to do a binary classification, what we're trying to predict, the model we're trying to create, is the labels are all going to be 0 and 1. So we'll always use numeric values, but we'll use 0 for like a false or negative, and 1 for a true or a positive for our binary case, or yes, no. Usually 1 for yes and 0 for no, right? So it makes sense then to introduce a squashing function. So that's the first thing. That's the way that I usually think about it, is that if we introduce the sigmoid function, this is known as a sigmoid. It's called the sigmoid because it has this shape here, right? So if you plot this out, so if you take the output from the same linear regression that we did before, so z is just meant to be the output of some function that can range anywhere from negative infinity to positive infinity. But if you take that output and squash it through this sigmoid function, the result is that the value is going to be constrained between 0 and 1. Okay, so the larger the number is, the closer to 1 it gets, and it's already relatively close once you get to 5. So anything bigger than that, it just gets really, really close to 1. Right? The same for 0 in the opposite direction. So anything less than -5 is basically 0 using the sigmoid function. Right? So that, that has a nice property when we're doing classification, is that now we can take the result of what we had before and put it through this additional step, and it will just directly give it into kind of a range that makes more sense for a binary classification, something between 0 and 1, right? And jumping ahead a little bit here, but so in terms of the cost function that we want to build from this, if the label is true or 1 and the output is 1, then we want the cost to be really low. But if for one particular item that we're trying to predict, if it was a 1, but we're somewhere over here, we're getting like a 0 or small value, we want that to have a high cost, right? So when we're doing binary classification using the sigmoid, we're going to also have to tweak the cost function a little bit in order to get what we want, right? So again, we can't use the straightforward root mean squared error. So I'm jumping ahead and also on that there, so we'll talk a little bit about that, why as well. So just a couple of things. There's a couple of different reasons why we do this. Another is that we can basically, when you're working with a binary classification using the sigmoid function, you can interpret the output as kind of a probability from 0 to 1. Okay, so the result will always be constrained between 0 and 1 when we put it through the sigmoid, but you can get values in between. So if you're somewhere around 0, you'll get somewhere around 1/2, right? So you can interpret when you're close to around here as being kind of uncertain. It's this equal of a probability. What my prediction I'm trying to do is equally likely. Maybe it's a 1, maybe it's a 0. We're just not certain. And the bigger or the smaller you get, the more certain you are that it's a 1 label or a 0 label. Okay? So one way this functions as is a kind of estimate of our probability or of our certainty. So whatever model that we end up ultimately building, so we're using H here from our textbook, and if you use, I remind you guys about Dr. Ng's lectures as well, so I hope people are using those. I find those really good, useful lectures. He goes into more details about the mathematics usually. If you want to have a deeper understanding of how some of this works underneath the hood here. So we usually use H as meaning kind of the hypothesis. So this is our function that we're trying to build, which, you know, given a set of inputs, X here is going to be what we think is the correct hypothesis or prediction for the labels. A little bit to our notation, this is actually the same thing that we did before for linear regression, okay? So all we're doing for an initial step before we put it through the sigmoid is we're just doing a linear combination of the features, okay? So this is a linear algebra notation, shorthand notation for we're just multiplying the input features times the theta parameters, times, you know, the slopes. I always think of those as the slopes. We have one value for each one of the features in X here, right? So these are both, you know, multi-dimensional vectors or arrays here that this operation is doing here, right? But, you know, really this is just multiplying each input times whatever the theta parameters are, and then, you know, this is really the multiplication and the sum of those, so you get one number, and so for like linear regression, that's be one number that is not constrained. It could be any value from negative infinity to positive infinity, so any real valued number. But then for doing logistic regression, we squash it through the sigmoid. So the sigma here is representing putting it through the sigmoid function here, right? So yeah, I mean, you know, a couple things that are good to be aware of from that our final, I mean, you know, our final prediction, if we're forced to make a prediction that we think is going to be a 1 or a 0, or think it's going to be true or false, you know, we have to do something because our actual prediction is going to be some number between 0 and 1, but not exactly 0 and 1. Right? So, you know, typically all we simply do is just threshold it. So at the end, when we need to make an actual prediction, we're going to just threshold it. So anything below 0 is going to have a prediction that's less than 0.5. So it'll be, you know, our best guess if it's, you know, 0.49 is we want to say, well, you know, I'm not very certain, but I would have to take it as 0 instead of a 1 is my guess. Right? Of course, the more negative it is, the more certain our prediction is. But yeah, anything above 0, it actually has a value above 0.5 on our sigmoid function. So, you know, typically we're just going to use that as the threshold here when we need to make our final prediction. So, you know, that has, you know, for the original value z below 0 or above 0, but when you think of that in terms of the sigmoid function, that comes to anything below 0.5, we guess is a 0, and anything above 0.5 ends up, we guess, or we say is going to be a 1 in our model here. Right? The root mean squared cost function that we use for linear, for a regression problem doesn't work well here when we squash it through the sigmoid. So instead, we want to modify our cost function. I think it's easiest just to think about the modification, then we can kind of go back and think a little bit more about why the root mean squared error doesn't work as well. So the idea is relatively easy to understand. So when we're talking about, and again, we'll only talk about binary classification, right? So we can later on extend this if we have a multi-class problem here, but let's just concentrate on where our problem that we're trying to model here is either a 0 or 1, a binary classification task. So in that case, all the things for the model that we're using to train with, the labels are going to be either 0 or 1. So for the cost function, what we want is that if the label is a 1, we want the cost to be really low if we're predicting a 1, right? So anytime we're over here and our label is a 1, we want the cost to be 0 or low. But if the label is a 1 and we're predicting over here, for whatever values our theta are, we want the cost to be high. But and you have to reverse that for the other case. So if the true value is a 0, we need to reverse that sense. So when the actual label is a 0, if we're predicting over here, we want to have a low cost because we're getting it right. But if the true label is a 0 and we're in whatever our theta parameters are, we're getting a 1, we want to have a high cost. So we have to build a cost function that does that, right? So the first step on doing this, we're going to really use a piecewise function. So we're going to actually have two functions that we combine using a little bit of some tricky kind of tricks, mathematical tricks. So we just want one function. We're going to use kind of the same function, just the inverse. But one function if the label is a 1, and a different one if the label is a 0 for our cost function here. All right. So we'll just use the log of our prediction. So the p hat is the prediction here. That's the result of taking our linear combination of some theta parameters times x and putting it through the sigmoid function to get a prediction for a value or a set of values here. So when the value is 1, we'll just use this. The log of the negative log of the p hat will give us a curve that looks like this, okay? But this is, a good cost function because what this is saying is that, remember, the true thing is 1. So whenever we're predicting a 1, we want the cost to be low, right? Because we're doing a minimization again here, right? So the negative log will give us basically 0 when we're outputting a 1, but the cost will get bigger and bigger, right? So if the true value is 1, but we're predicting like 0, then essentially the cost gets really big really fast the closer you get to 0 here. Right? And we really do the same thing for the case. So every place where y is a 0, when we're training our model, we need to predict a 0. We just use the 1 minus our p hat. So that will flip the curve here. But that'll give us a good cost function for the y equals 0 case, because again, the cost is essentially 0 when we're predicting 0. But the cost begins to rise, and it rises rapidly if we're predicting 1 when we should be predicting 0 for the set of theta that we have. Right? So I don't know if it's fair to call this a trick or not, but it's easy to combine those. So we can write one expression. This is our cost function. We should go back and compare this to the cost function that we had before for straightforward linear regression later on. But for our cost function for logistic regression, we're basically doing what we just showed there. So we just multiply by y. So when y is 1, we only do this term. Because when y is 1, this will be 0, and that will go away. And when y is 0, likewise, that will go away, and we'll only be doing that term. If we look at it, for the y is 1, we just want the log. When y is negative 1, when y is 0, we want this term over here. Right? The negative log that we did got factored out here, so that's why we have a negative at the front of this expression here. Right? But this y and 1 minus y basically allows us to use the piecewise function in a single expression. But we're doing that over the whole set, so this is the same as what we did when we did the root mean squared cost function here. So here we're using the negative log for the cost here, but we have some set of samples, And yi is what the label is for each ith sample. And this allows us to calculate. And so if all of them were correct, we're basically always going to get costs close to 0. So this would sum up to 0 here. And if all of them are really bad, if we're always predicting 1, 1 should be 0, or 0, 1 should be 1, we're going to get really high costs when you sum up over all the samples, which is what we want. So, right, we're just taking the average of that. So if we have m samples, we divide by m. That's kind of the average cost that we have for however many samples that we're doing this for. So it's a little bit beyond the scope of this course, but one reason why there's other things we could have done in terms of defining a cost function that would work with our binary 0 and 1 classification here, other than the logarithm. Probably the easiest thing, the most straightforward thing to understand is one reason why this is commonly used is because it is easy to take the derivative. So we can analytically take the derivative of this. That's what this expression is. You don't have to really understand what happens here. Just take it as a given that the derivative of the cost function that we define comes up with this expression here. All right. So, but since we can analytically derive our derivative of our cost function here, we can do the same optimization that we talked about before with this expression. So from this we can tell for any particular set of theta with respect to each one of the features, whether we need to, which direction we need to go in order to get to a smaller, a lower cost. Right? So this serves the same thing, the same function that we had before, in order to do an optimization over the theta for each one of the features, and get thetas to the location where they will have the smallest, the minimal cost possible. Right? And we can do that without having to explore the infinite number of possible combinations, because this derivative tells us which direction to go for any particular set of theta, which way we have to go to lower the cost. So we can optimize using gradient descent or a similar cost function. Okay? Yeah, I just wanted to compare this. I mean, you may not remember, but let me bring that up real quickly here. So when we talked about, where was it? It was either in 5.2 or 5.1 or 5.2. So here was our expression. Again, this one is a little bit easier if you've taken a course in calculus. We're basically doing the derivative of our cost function here, although we've got terms that are represented using vectors, so linear algebra here. But it's not too difficult to understand how this is derived. But another good thing to do is compare this to the derivative of the cost function that we did using the logarithm. So our cost function for the logistic regression, right? So here the derivative was, we're simply, in here, that is really just the difference of our predictions. So theta times x minus the labels. So that's the difference. So we were using the sum of the squared differences. But if you just take the differences times the feature, the j feature, with respect to j, that gives you your gradient, your derivative at each step here, right? And we're just averaging that. Right? So, so you really, the real reason why we use this cost function for logistic regression, for classification, is the math works out that you really get exactly the same formalization for the derivative here. Right? The only difference is that we're taking our predictions, theta times the input x's, and we're squashing them through the sigmoid function. But otherwise, this is the same expression that we had before. Well, there's some other slight differences, but it's basically the same that we had before for the derivative. So that means that, for example, we showed an example of implementing gradient descent by hand before. So you can do gradient descent for this cost function for logistic regression with almost no modifications. The only thing you have to change is when you calculate the gradients or the derivatives, just squash through theta. Otherwise, it's pretty much the same as what we had before, right? Which makes it nice, right? So all the stuff that we talked about for optimization, for linear, for doing regression problems, we can use the same idea, the same formalization, using this cost function to do a classification task. Okay, so with that in mind, then we can talk a little bit more about decision boundaries. So we've come across this concept before. So when we visualize the result of a regression problem, like you did for the assignment 3 that you just completed, the result is a line, or it's going to actually be a plane if you have more than one feature. All right. So, but for our assignment 3, we actually really only had one feature, although we looked at the higher powers of it. But it was a line, a polynomial. So for a classification problem, the result of optimizing the cost function that we had here is you're going to have something that divides. So again, we'll just talk about binary classification. We'll just think about binary classification here. So the resulting thing that you get is a boundary, is a division. So on one side of that division of the decision boundary, you'll be predicting that your class is a 0 or a false, and on the other side you'll be predicting it's a true or a 1. Okay? So, and it might not be obvious, but really the logistic regression here, this decision function here, makes a linear decision boundary. Okay, so later on we'll look at some more complicated cost functions that can give you a nonlinear decision boundary. But here, if we optimize this using this gradient, the result will be a line if you only have 2 features that you're visualizing the decision boundary on, or it will be just a plane. It will be a linear plane or hyperplane if you have more than 2 features. So that basically, if I can go back here just real quickly to this, that basically comes from this here. So there's going to be a line somewhere where the decision boundary, when you visualize it, is going to be the place where everything where you're predicting a 0. So where the result for whatever our theta are end up being less than 0 will be on one side of the decision boundary, and everything where you're predicting a 1 will be on the other side. Right? And the division between those will be linear for the cost function we're looking at right now. Okay. So yeah, I believe this came directly from our textbook. So we can go back to the idea. We did this for actually the assignment before the one that you guys just completed, where you may or may not have quite understood what we were doing, but we kind of walked you through by hand of calculating the decision boundary that logistic regression was making. So we can do the same thing here, but we might be able to better understand what's going on here. So I don't remember if we've looked at the iris data set before. Our textbook uses this a lot for examples for doing things. So iris is a classification problem. It's got 4 features. The irises are flowers, so it has the measures of like the petal length and width and some other, the sepal, I don't know what the sepal is actually, but some other, the length and the width of another part of the flower. And in this case, it's actually a multi-class classification problem. There's 3 different types of irises. I'm sure we got it here somewhere, Virginica, but we're going to turn it into a binary classification here. So here we're just changing it down so that anything that is Virginica, so the label 2 was Virginica in this iris data set, and 0 and 1 were the other 2 types here. So now 1s are going to be Virginica, and 0s are going to be not Virginica. We're going to try and build a regression for that, right? So and here, and also just to completely simplify it, this is the example from our textbook, but we'll only look at a single feature so we can visualize the decision boundary. So yeah, just looking at petal width and seeing what we come up with as. So for classification, if you have a single parameter, you end up with just a point, a line below which you're going to predict Virginica, and above which you're going to predict not Virginica. So I guess it's the other way. So yeah, so all these things here, if our decision boundary ends up being there, so approximately 1.66 for the petal width here. So anything above that, when we put it through logistic regression, will get predicted as a 1, or a Virginica, in our data set here. So if you actually plot the not Virginica, you'll see that, of course, you can't get a perfect decision boundary with this single feature. There is some overlap. So, so if I moved it over here, I would get all of the not Virginicas correct, but I'd be getting more of the Virginicas wrong. I'd be misclassifying them as not Virginicas, and vice versa. If I moved it this way, I could get all of the Virginicas correct at the cost of having more of these misclassified as Virginicas when they're not. So the decision boundary, the reason why it ends up here is that it does minimize the cost. So we only end up with 5 misclassifications. There's probably more. We're not showing everything in the data set here, but here there's 2 misclassified here, and 3 down here, up here that are misclassified. So if you walk through how we got that, so we did the thing that you should be familiar with for fitting a model using scikit-learn. So we've got a logistic regression model, and we fit our data. Our data is very simple in this case. We've got one feature, so the third column in the data set, and we've got our binary. So we made it a binary classification pass. That's what our Y is here. So here is where we're figuring out what the decision index ended up being. So basically, we find the first location that's greater than 0.5, and that's the, that ends up being the value for when we fit the logistic regression here, that we make the decision between Virginica and not Virginica on this model here. Right? So, you know, I mean, that's not too interesting. If you visualize this with two features, so yeah, the next thing the textbook does here, we take two features instead of one, so that's the pedal length and the pedal width, but do the same thing. Right? Here, we're using like a contour plot in order to see the levels of the of our model that we end up fitting here. Right? So in this case, the contour plot, we show different levels here. Where do we control that? Yeah, by specifying it's that there, I believe. So we have 10 different levels. So we end up showing where our predictions go from like 0 to 1 in increments of 1/10. So it's either 0.1, 0.2, 0.3, 0.4, 0.5, and so on here. Right? So when we're using two of them, pedal length and pedal width, we end up with a line in 2 dimensions. That ends up being our decision boundary, since the model that we're fitting here is a linear model. And yet, you know, we talked about this before when we first talked about classification. We could, you know, if we needed to tweak the ratio of false positives and false negatives, you know, so like our precision and recall rates, we could use a different decision boundary, but the default is just to use 0.5. So for 0.5, that ends up being the actual decision boundary. So again, there's no linear separator that will get all of the Virginica on one side of it for these two parameters, and all the not Virginica on the other side of it. But this ends up being the one that minimizes the cost, that minimizes the number of incorrect classifications. So we got a couple of not Virginicas on the, so everything up on this direction, the predictions end up being above 0.5. When we, you know, for our theta, we've got two theta parameters, theta 0, theta 1, and when you multiply those that we optimized and put it through the sigmoid function, you know, we get things above 0.5 going to be on that side of the line, and things below 0.5 are going to be on that side of the decision boundary line that we end up with here. Okay, still got plenty of time here. So, yeah, so let's try and go through this a little bit here. So everything up to this point from the textbook or from this notebook is the basics of using this new cost function for logistic regression. Okay, so the things that kind of remain is we have to think about, one of the big ones is often we have problems that are multi-class, right? So even the iris data set here, we turned it into a binary classification task, but really what we would like to do is have a model that can predict one of the three different flower types. So it was Virginica, Setosa, and a third class. I can't remember. In the iris data set here. Yeah, let me try to get into softmax regression. So you might run across this. Softmax is supported directly in scikit-learn. So softmax is really an extension so that you can directly do multi-class classification problems using the same cost function. Using just a slight variation of the cost function that we just came up with for a binary classification task. So so yeah, this is for multinomial or basically multi class problems here. Again, I don't want to get too heavy into the notation here. The way I usually think of it is basically all we're doing is we compute, if we've got three classes, so K is going to be the number of classes here. If we have three classes, K would be 0, 1, or 2 here. What this expression ends up doing is we end up then with three probabilities. So the probability, I picked 3 because we're still kind of using the iris data set as our example here. So we would end up with 3 numbers, 3 predictions using this softmax approach. Our prediction or our probability that it's Setosa versus Virginica versus the third iris type that we have in the data set. And all this expression does is it's using the same cost function that we had before, but this will normalize it basically so that the sum of those 3 probabilities, if we have 3 classes, sums up to 1. Right? So if we're really certain that it's a Virginica, we might end up with like a 0.95 for the prediction that's Virginica, and then the 0.05, the 5% would be spread between the other 2 that are less probable. So anyway, if you work through this notebook, it tries to give you a little bit of an intuition of how this expression works to like normalize a multinomial. So when I have multiple predicted outputs. So for example, think of, in this made-up example, think of each one of the rows as a sample number, where we've got multiple samples around each and in this case we've got 3 different classes. So again, we're using the 3 classes that we'll call class 0, class 1, class 2 for the K's here. Right? So if you put them through the score function before you do it through the sigmoid, that's what these are supposed to represent. So that's just the score when you multiply it by theta and sum that up. So in this case, for softmax, we're actually going to have 3 sets of theta parameters, if that's not clear here. So, what's happening here, the score is, this notation is it's kind of hiding the fact that what we're really doing is fitting 3 logistic regressions, like we did before, one for each one of the separate classes. So that's why there's k sets of thetas here, one for Setosa, one for Virginica, and one for the third iris data set. So, assuming that you have those, this is just the result before you put it through the sigmoid for 3 different samples. So that was, in each column is the output value that we have for the result, so the raw values that we have for each of those. So, we're using the exponential here. So, we're just showing doing the same term. So doing the exponential and then doing the sum of all of the 3 exponential outputs that we have here. All right. So, so that's all this is. So that's just that's like the top of the expression we have here. That's the sum that would go on the bottom. And basically then, if you, that's the sum for actually each sample, each row here. So the sum for these 3 was, you can see it's 90. So basically then, by that expression, if you just divide that by the sum, that normalizes it, right? So this is kind of the important thing to kind of understand what's happening here. So for the 3 separate logistic regressions that we have, by using the softmax function, we normalize it into, so for like this first one, we were pretty much certain it was the class, the k equals 2 here. Where for these, if you look at the raw values, or like the bottom one especially, they were all much more closer to being equal. So we see like 0.33, 0.25, 0.41. But the sum of each one of those should be 1. Right? So like if you sum up all 3 of those, so if we had to pick, our highest probability was that k equals 2 class there, the 0.41. But it's still pretty high for the other 2. So yeah, to tell you, we actually, when you use softmax regression, we actually directly are using this as a cost function and the gradients of that. So, but you can find the derivatives. So that's kind of what this is showing here. I don't think it's necessary that people understand the nitty-gritty details of all this. I think the big picture, the thing to understand about this is that there are, this is one way to generalize the logistic regression for if we have more than more than 2 classes. Okay? So we can use the softmax. It works out in a similar way. So this really is the cost function for the softmax, which was modified here. So this is a little bit different than we had before because we've got k of these expressions. But the reason why the softmax function is so useful is if you look at the case where k is 2, where I just have class 0 and class 1, this pretty muchly simplifies to the binary classification case, right? It's a roundabout way of coming through it, but the softmax function is equivalent. This is just more general, so it allows us to do the same kinds of things that our first logistic regression cost function does, but extend it to more than 2 classes here. But yeah, so for logistic regression in scikit-learn, it has support for doing multi-class classification using softmax built in directly to it. So yeah, we'll look at. I guess we save it till after the break here. We'll look at some other ways of implementing a multi-class classification. So another way is just to directly create multiple models and then do something to combine them. That's what's being talked about here. So yeah, the default used to be to use multiple models and use like a one versus all. But now it does use softmax by default, I guess. So if you do logistic regression on the full here, I think we've gone back to using the full iris data set. Yeah. So where we've got 4 features and we've got 3 different flower types, so 3 different targets in the data set here. But here, if you read through this, it used to be there was a multinomial parameter, but now we've got just something called multi-class, which has been deprecated. What do they say about that? So anyway, I mean, right, this is some details, but yeah, if you read through the softmax here, I mean, that's basically what's happening here. So yeah, the default is it depends on the solver that you're using, but the default is probably going to be using softmax now. But you can explicitly. It might not work depending on what kind of solver you're using, like it's saying here. But the OVR is the other one where it builds separate binary classification problems, and we'll talk about that later. Right? So we've got that in a later set of lecture notebooks as another way to tackle. If I need to do classification with more than 2 classes. All right. So yeah, as a final thing, I mean, again, here we're using the trick of this comes from the textbook. But yeah, using the trick of doing contour plots so you can visualize. We are using the softmax, so we are using the multinomial classification here, but with 3 classes, we end up with linear decision boundaries. It's still linear decision boundaries between the versicolor was the third one I was trying to remember. So between the Virginic versicolor and the Seposa that we have here. But you can see with that same kind of trick of doing a contour plot of the decision boundaries that we get. So up here, what the triangles are the Virginica. So anything kind of above these decision boundaries here and here will get correctly classified as Virginica. We got a few things misclassified, so we're only showing 2 of the 4 features here. We are able to completely separate the setosa from the other 2. So there is a decision boundary on a couple of these features that allow you to correctly, completely get all those to one side of the decision boundary. And that's maybe that'll be the last thing. So I should have emphasized that a little bit more. So when we talk about support vector machines after the break, we'll talk about this concept of linear separability. So that's kind of important for classification problems like this, right? So, but this is an easy illustration of that. So if you can make a linear decision boundary that completely separates like a binary, so 2 classes on one side and the other, then it's linearly separable. Those are simple. So most real classification problems are going to be tougher than that. They won't be easily linearly separable, at least on like one feature or a couple of features. But things that don't have that property, that you can't get a single linear decision boundary to separate those, are not linearly separable. Right? So, and you know, if I want to do better performance-wise on building a classifier for things that aren't linearly separable, I either need to add more features so that maybe in higher dimensions it's more easily separable, or I have to start using a nonlinear decision boundary. Support vector machines allow ways to easily give, much more easily create nonlinear functions, nonlinear decision functions for a set of data. Okay, yep, so we went through that whole notebook, so I'll go ahead and stop there for today. Probably will review some stuff from the assignment 3 on Thursday. And I think, even though I had it in a notebook later on, I might talk a little bit about the other, jump into some of the stuff on the other ways of doing multi-class classification that were mentioned here in this chapter from the textbook, but we haven't talked directly about those yet. So. But yeah, we'll do that on Thursday then. So, maybe also begin talking about the test if anybody wants to ask some questions about the midterm test for next week. So, all right, that's it. Save that.